Hi, hello everyone. How was your quiz too? Am I audible?
Yes, you are
Good
audible.
evening, ma'am.
Good evening. How was quiz two? How did you guys find it? Easy or doable or difficult?
It was easy. Easy.
Okay, it's quite an easy paper. I hope everyone was able to kind of do most of it. Okay, so this session is for week 9 summary. So we'll be discussing week 9 today, and basically the basic summary of week 9. So let's start with the local maxima and local minima. So local maxima, local minima is basically graphically, if you look at things, okay, let's first give the definition of local maxima or local minima. Local maxima, when you have a function, this is the graph of the function. So you'd say that this is the domain, right? This part is the domain. If your function keeps going, then this is the domain of definition of your function, and then this thing that you can attain will be the range, right? So your local maxima minima is actually a part of your domain. So it's in your domain. First thing is this, and then what does the definition say? It says that it's the point in your domain. Let's say you have A, so it's A is local maxima minima should put this in bracket. Local maxima, or respective, this one is minima, if there exists an interval around, this is the symbol for there exists, or you can just write if we have an interval containing A. So let's say if this is, we say that A is a maxima, or let's have like a nicer graph to see things. If you have something like this, if this is your graph, then A is called a maxima or minima. Let's say this is a point A. Then you need an interval around A. That means you need an interval in the domain, obviously, that contains A, such that in that interval, the value of the function is less than FA. So if this is your FA, this height is FA, right? This entire height is FA. You would want an interval around A such that every height in this interval, that means every value corresponding to this point, value corresponding to this point, and similarly value corresponding to every point in this interval needs to be lesser than this FA. And you can see that if you take this to be the interval, then every value from here to here, this height, this height, this height, this height, on the right side to this height, all of them are lesser than FA, right? That's why we'd call it a point of local maxima. Local maxima basically means that in the locality, it should be maximum. In one of its localities, it should be maximum. So this, you have a locality here. In this locality, so if this is your A point, then in this locality, this one, this height, this point will have maximum value. That's why we call it a local maxima. Similar is the case with local minima. So if we have an interval, let's call it BC, such that A is in this interval and f of x is less than f of A. That's how we define it, right? If we have to write this thing, this is what we saw graphically, that we need an interval around A. Let's call that interval BC. We need this interval, and every value, the function's value at every point in this interval should be less than FA. So fx should be less than FA for all x belonging to this interval B, C, right? Is this thing clear to everyone, the definition of local maxima? Or for minima, you will need fx greater than FA. So for minima, this changes, and for maxima, it's this. Is this clear to everyone? So let's say if you look at the examples graphically, we'll see some graphical examples. Let's say you have this graph. Then this point corresponding to this height. Let's say this point is A and this height is FA, right? So this point will be A comma FA, right? Similarly, this point is, let's call it B, or then this is B comma FB. Let's call this C. Then this point is C comma FC. And same is with these ones, right? Then A is a point of local, these two. These are local maximas. This is a local maxima because there is a neighborhood, or you can say there's an interval around A where this has maximum height. A has maximum height. Everyone else here has lesser height than FA. Same is the case here. Same is the case here. And same is the case here. So all of these points, this is a local maxima, this is a local maxima, this point is also a local maxima, this point is also a local maxima. And about local minima, this one is a point of local minima, B is local minima, this point is a local minima, and then this point is a local minima. And if this is your domain, let's say your domain is this. From here to here. Then the very obvious local minimas are,
I missed that starting point. Can you repeat?
which one?
The starting concept.
That's just the definition, because this one, right?
Yeah.
Okay. Local maxima, local minima means when you have a graph, what you do is, local means you need, if you're calling this point a local maxima, that means first thing is you need an interval around this point such that this function has maximum height at this point in this interval. That means, let's say let's take the example of x square. So if you have x square, your x square looks like this, right? Or let's say, okay, let's take this one only. If you have something like this, then what it means is local maxima means that you need a point. If this is your domain, local maxima is a point in your domain where around that point you need an interval. Let's say this is your interval. You can choose any interval, this interval or a smaller interval. We just need one interval such that.
Ma'am, the peak point
Yeah.
there is an intercept that is called local maxima.
Yeah. This is called local maxima if there is a locality around this point where the maximum height is attained at this point. So the maximum height is attained here, right? If you look in this interval,
Right.
this point
Yeah.
has this height, this point has this height, and all the points from this point to this point has height from here to here, right? The maximum height is attained here in this interval.
Yeah.
You could have chosen smaller interval, you could have chosen a larger interval, that's fine. But you need to have one interval, only one interval, that's it. Now in this case, you can't take this interval. Or maybe you can take this interval too, but you can't if you have something like this. Let's say your graph looks like this. Then the interval that you should be taking is, you can take this interval. This interval works fine. This interval works fine too. But if you take this one, this does not work. Then this won't be the local maxima, right? So because
Yes.
maximum is attained here. So you'll have
So
to
we have given the graph in the question. or not?
So this is just how you see the local maxima minima concept graphically. There are other ways to find local maxima minima without looking at the graph. We'll come to that. But if you're given the graph, then this is how you tell if it's a local maxima or local minima, or if it's
And so
neither.
the
Right?
graph on left is the local minima, right?
This one,
Yes.
which one? No. See, if you have something like this, then both of these are local maximas. This is also a point of local maxima because you only need one locality around this point. That's it. Where the maximum height is attained at this point. That's what you want. You want one interval around this point where maximum height is attained at this point. Now, if you have this interval, you have found one interval, right? Where the maximum height is attained at this point. So this is a point of local maxima.
How
This
we
is
determine that this is the interval and this is the maximum
you
height?
can
Like
choose
maximum height,
any interval. You can choose any
okay.
interval. That
Okay.
interval you have to find. If you're able to find one interval where the maximum value in that interval is attained at this point, then you can say that it's a local maxima.
Like in the right hand side, the highest curve where the graph is attaining the highest value, won't it be a global maxima rather than calling it the local maxima?
That's also, this is also a local maxima and it's also a global maxima. This is both. We'll come to global maxima, but for now, this is, both of these are local maximas. And
So
this
there
one is a
won't be
local
any,
minima. Yeah.
there won't be any local minima in this, ma'am.
Yeah, this is the local minima, right? You can find one interval here where the maximum value is attained at this point, right?
Only
Yes.
one is there is only one local minima, right?
Yeah, this one
In
is
this
one
graph.
local minima. But if you have like this, we'll come to this point. If you have a fixed domain, then you can check an endpoint too. What happens there is your endpoints are included in the domain, right? This is your domain and the endpoints are included here, right? This is one endpoint included in domain, other endpoint included in domain. So ideally, you should be checking for these points too. This is also a local minima. This is also a local minima.
It depends upon the interval.
Yeah.
So in case of maxima, if in the exam, if they ask about the how many local maxima are there and how many global maxima are there. So one, for example, in the previous diagram,
This one,
no, the last diagram, last
this
diagram
one,
you brought.
this
No,
one.
after, yeah, this one. So if they are asked about how many local maxima are there, so what will be the answer?
It will be two, right? This is one and this is the other one. Only two.
Okay, so we have to count the global maxima as well.
Yeah.
Okay.
And okay, we'll come to global one later. So this is the definition of local max. The definition mathematically is this, but you don't have to remember all of these details because you won't be asked definitions. So you can just remember the one that looks highest in a particular interval around it is the local maxima, and the one that looks least in a particular interval around it. If you can find such interval, then it's a global minima, a local minima and a local maxima. Is that all right?
Yeah, sure. Got it.
Okay. Like let's say
Ma'am,
you
I have a
have,
question.
yeah.
Yeah. So if I have a one-on-one function, then I might not have the maxima or minima, right? Because the one-on-one function is either decreasing or increasing.
I mean your see, one functions are not necessarily, you're saying one functions are either increasing or decreasing. But if you have something like this, let's say I have this and then I have this, then this is a one function, right? And it's not increasing or decreasing in the entire domain. If this is the domain and then this is the domain, then it's not increasing or decreasing in the entire domain, right?
Yeah, right.
So
Okay.
it's changing,
But
this
ma'am,
function is
if
changing
there's
monotopicity. Yeah.
but if there is no turning point in a graph, then there will be no maxima or minima, right?
No turning point. No, this one has a turning. This does not have a turning point, right?
Yeah.
Where's the turning point here? But this is still a local maxima. This is a local maxima. This is also a local maxima. This is a local minima. This is again a local minima. Right?
Got it now. Like endpoints also count.
Yeah.
Yeah, okay.
So the one thing that you were talking about, if you will take 1 plus continuous, and continuous stuff is in your syllabus, right? So if you have a 1 function and it's continuous, then you can say that it's either an increasing function or a decreasing function. Increasing, in fact, this is a theorem, increasing or decreasing monotonically. And then you can say that it won't have a turning point, or it's not going to have, it can still have, by the way, if this is the case, then it can still have, if this is the domain, it can still have maxima and minima. This is the minima, this is the maximum.
The endpoints.
Yeah.
Okay. Okay. Yeah. Okay.
Okay, then let's move to some examples that are not just graphical. So let's take sin x, very popular example. So if you take sin x, or let's take x squared first. So if you have x squared, the graph looks like this, right? So graphically looking at it, you can just tell that what's the local maxima? Your domain is R. Local minima is 0, this point. And we don't have, does not exist, right? If it's R, the entire real numbers, then the local maxima does not exist. There's no local maxima. Because every point you will take, if you will take this point, then you cannot find any interval around this, where this is the maximum, this attains the maximum number. Right? You can always find something which is greater than this, no matter how small you take the interval. Is that okay? You
Okay,
can,
because
without
it
delving
doesn't
into
have any
definition.
endpoint.
Yeah, in other words, you can understand this as it does not have any endpoint, so it keeps increasing. Local maxima means you need at least one interval around that point where this is the maximum, your maximum height is attained at this point. But if it's increasing as it is here, then you cannot have a maximum point, right?
Yeah.
So if you have x cube, what about this one? What's the local maxima? And local minimum.
It also have local maxima or local minima.
Does this have a local maxima?
No,
No, I think.
not because
No.
it's also don't have any endpoints. It's keep increasing
Yeah.
or decreasing.
And what about local minima?
Yeah, it's same about local minima because it is also
Same.
decreasing
Right.
at the same time.
Then let's do sin x. If you have sin x curves, then the sin x curve looks like this. They're all equal heights. This is also height 1. This is also height 1. This is -1. They're of the same height. This is pi by 2. This is 0. This is pi. This is 3 pi by 2. And it keeps going on in this manner. So, and same is the opposite side. So if these ones are odd multiples of pi by 2, these ones, and these ones are multiples of pi, then this is pi, this is 2 pi, this is 3 pi, this is 4 pi. Then what are the local maximas and local minimas?
it also doesn't have a local maxima.
Why?
Because
It
because
has a
there-
local maxima, right? We're not going to the end. Okay. We'll come
because
to
it
these
is
examples
like
again.
equal in. No, ma'am, you said every interval is equal. Like it
No,
has
I didn't
minus
say
one
every
and other.
interval. I said you need, that's why the definition is important. If you say this is local maxima, then you will need at one interval. You only need one interval. You can choose that interval. You're free to choose that interval. You decide that interval. We just need one interval around this point A such that your fx is less than fa. That's it. So we want one interval around this point. If this is a local maxima, then you will get one interval. You might only get just one interval you have to find. So only one interval you have to find. Let me call this interval I. Such that every point in this interval, the value at every point in this interval is less than the value at fa. So like this. If fa has the highest value in this interval and every other value at these points is less than fa, then it should be like this, right? So this is what you want. An interval around A where the value of this function at all points in that interval should be less than fa. Now, if you'll come to this one, let's do this properly. You have this point, right? Let's take pi by 2 and let's take an interval, this one. You can choose any interval. You can choose this. You can choose this. But the condition is choose one interval such that the function's value in this interval. So at this point, for example, at this point, this is in this interval, the height is this. At this point, the height is this. The condition is all these heights should be less than the height at this point that you're claiming to be the local maxima. So if you take pi by 2, you can have an interval around pi by 2. For example, take this interval. Now the height at pi by 2, the value at pi by 2 is this, right? F of pi by 2. This is f of pi by 2. And every other value of this function in this interval is going to be less than pi by 2, right? Now, if you choose this interval, then this might not hold true, right? If you take a bigger interval from here to here, then this condition will fail. That's why it's very important to choose the interval carefully. Choose this interval and you're good. So pi by 2 is a local maxima. Same is the case with 3 pi by 2. This is 3 pi by 2. Choose this interval around 3 pi by 2. Now look at the heights in this interval. This is the height. This is the height. Height means the function's value in these points, in the interval points, right? So, okay, this is -1, right? This is not it because it's negative. So you can first you've taken pi by 2, then you can take this one. So this one is 2 pi plus pi by 2, which is 5 pi by 2. So the next point will be 5 pi by 2. Then you will have the next one is 7 pi by 2, but it has value -1. So the next one is going to be 9 pi by 2. Then 11, leave the 11 one, and then you will have 13 pi by 2. And so on. And for the local minimas, where are the local minimas? Let me draw this clearly. We have this thing, right? This has height 1. That means the function's value at this point is 1, which is the greatest in this interval. Similarly, here the function's value is 1 at this point, which is the greatest in this interval. Similarly, here the function's value is 1, which is the greatest in this interval. This is pi by 2. This is 3 pi by 2. The next one is 5 pi by 2. The next one is 7 pi by 2, this is 9 pi by 2, and it keeps going on like this, right? So this has maximum value 1, the local maxima, pi by 2. Then 3 pi by 2 has value -1. So it should be here, right? Then you will have 7 pi by 2 again here, because it has value -1. Is that okay?
Yeah.
So you just have to find the trick, not the trick, that's the definition. Just find one interval, any interval of your choice, where the maximum value is attained at this point. Then you can say that this is the point of local maximum. Same is the case with local minimum. Okay, then let's move to tangents. So if you have tangents at these points, let's say you have turning points, we know that your turning points are, or let's first discuss your critical points. So your critical points are basically, let's say your function fx, and you have to discuss the critical points of this function. So the critical points are points where either f is not differentiable or f dash x is, or f dash a is 0. Or let me just write a is a critical point of f if either either f is not differentiable at a, or f dash a is 0. So let's take the first one is this. Let's take the example, let's take example sin x only. If you have sin
Ma'am,
x,
this is the definition of critical point which you have just written.
yeah, this is the definition of critical point. What are you exactly asking?
No, I was just asking if it's the definition or not.
Yeah, this is the definition. A critical point is a point where either your function is not differentiable or its derivative is 0. So either the derivative does not exist at that point, or if the derivative exists, then it should be 0. That's the
Okay, ma'am.
definition for a critical point. So let's take sin x, for example. If you take the derivative of sin x, it's cos x, and cos x is 0 at pi by 2, right? Or the multiples of, odd multiples of pi by 2, right? Pi by 2, 3 pi by 2, 5 pi by 2. So these are odd multiples of pi by 2, and so on. So the critical points for sin x are x equals to pi by 2, 3 pi by 2, and so on, so on. There's also another condition which says either the derivative is 0. So derivative 0 is this, right? If you have to find the critical points of sin x, then either you take the derivative of sin x equals to 0, and then you find all the x such that the derivative of sin x is 0. Or you find the points where sin x is not differentiable, and then you combine both of these points, right? You take the union of the sets, right? So the points where the
Ma'am,
derivative of sin x, yeah.
I didn't understand this point.
If you have a function, let's say you have fx, and you have to find the critical points of fx, then the way to do is first find the derivative of that function and see where it's 0, right? Because all the points where your function's derivative is 0 comes under critical points, right? That's one.
Yeah.
And then there are some other points too that can be critical points. Those points are where your function is not differentiable. So this is first one where derivative does not derivative is 0. F dash x is 0, right? This is the derivative of your function cos x, and you've equated it to 0 to find the critical point. Or what's the other way? This is not or. This is not like you can use this or this. This is like you should use this to find some critical points, and the second one to find other critical points. There are some critical points that are not here, that are not listed here, that you can't find using this, right? So for that, you need to find the points where the derivative of sin x does not exist. So are there any points where the derivative of sin x is there a point where sin x is not differentiable? If you have already seen the graph of sin x, it looks like this. Do you think there are points where this function is not differentiable? Differentiable in simple graphical terms means that it's not smooth. It has something like this or this.
No.
This function seems
No, not
perfectly smooth, right?
Differential.
Keeps going on. So it's differentiable. And sin x, the derivative of sin x
cos x.
is cos x for all x, right? For all x belonging to real numbers. That means it's differentiable for all x. That's why this is the derivative, right? So this is
Yes.
differentiable everywhere. You can also use the definition of differentiability if you want to find out, but that's not needed. That means there are no points where sin x is not differentiable. Right, but let's say you have another function. Let's take this example. Let's say you have a function as mod x for x less than for x less than 3, and for x greater than 3, let's take this to be 3, or not 3. Let's take this to be, let's try to construct a function like this. Let's say you have this. This is 3 point. And 1 second. Let's take this to be 4, or yeah, 4, and let's take this to be x minus 4 squared here. So a graph then looks like this. How do you draw this graph? This is for x less than equals to 3. Your graph is mod x. So it's this. Till this point, it's this. And then at x equals to 3, you have this thing. X minus 4 squared. How do you draw the graph of y is equals to x minus 4 squared? The vertex is this, right? The vertex is 4, 0, which is this point. And let's take minus here. This is a downward graph. Or let's not take this one because then it won't be a function. Let's take sin x from here. For x greater than 3. We don't know where 3 lies. 3 is, what's 2 pi? Pi is 3.14, right?
Yeah.
Yeah, so this somewhere here will be pi, and this is At this point, you will have 0. So it's something like this. Is this okay? So till x equals to 3, till this point, you have mod x, and then you have sin x. So if we'll talk about, and we were talking about critical points for this function. Let's talk about critical points for this function. So critical points are points where function is not differentiable. Union points where derivative is 0, right? What do you think should be the critical points for this? Does anyone want to give this a try?
For sin x, maybe all the turning points will be the critical points.
Yeah, okay. These are, but let's go by the definition. Let's not get into turning points and all. Let's go by the definition, right? So
Three
let's
and
first
four.
try to see where this function
Okay,
is
let's
not
derive it.
differentiable.
At 3 and 4, the curve is not differentiable.
Yeah. 3, this point, because this is where your function is not even continuous, right? At 3, your function is not even continuous. That means it's not differentiable here. That means it's a point where your function is not differentiable. So one of the critical points is 3. What about 0? 0 is also a point where your function is not differentiable, right? So 0 should also be a point where your function is not differentiable. 0, 3, and then what's next? Are there any other points where your function is not differentiable?
4.
So that's it. Everywhere else your function is differentiable. These are the only 2 points where function is not differentiable. How do you identify them solely on the basis of graph? 1, because at this point, for 3, it's not even continuous here. Your function is not even continuous at 3, so it can't be differentiable here. And for 0 point, you have a sharp turn here, a sharp corner here. That's why it's not differentiable. And mod x, we
Ma'am, on
already know
3,
mod x is not, yeah.
on 3, they like it is the endpoint.
It's the end point, but if you have to give an absolute reason, you can just say that the function is, this is not an end. How do you conclude? These are not
Like
called endpoints. It's an endpoint of the interval in the domain. So if you're saying not even that, it's not an endpoint anywhere. Or the
yeah, okay, it's not an endpoint in the total graph, but like the sin x you draw in that scenario, it is the endpoint. I'm saying that.
yeah, so you can say that it's not, that's the main reason is it's not continuous here. And you must have done this theorem that if a function is not continuous at a point, then it's not differentiable at that point either, right?
So, yeah, so like just like you have described, if there is a graph uh, mm, of sin x, then the endpoints we can call that critical points because there is no continuity. Okay, that is not continuous at that point.
It depends. If you have something like this, if your sine function, if it was after 3, it was sin x, and before 3, it was something that went like this, some other graph which went like this, then you can't say that it's not, then you'll have to check, right? You'll have to check the differentiability because
Yeah,
now
in
it's
that
not breaking here.
case, it is continuous. Yeah, it is breaking, then only we can call that
Yeah.
it is
Not
not continuous at
differentiable.
that.
Not continuous,
Yeah,
that's why
not
not
differentiable.
differentiable. So these are the 2
Yeah.
points where your function is not differentiable. Then there are points where the derivative is 0. So that the points where your derivative is 0 is this function. If you have mod x, then mod x looks like this. For x less than 0, it's minus x, and for this it's x, right? And by now you should know it very well that this function is differentiable everywhere except at 0, right? And obviously this one, this endpoint. Everywhere else it's differentiable, and about its derivative being 0. So its derivative is going to be -1 for this branch. For x less than 0, for any point less than 0, the derivative is -1. For any point between 0 and 3, the derivative is 1. So it's nowhere 0, right? Our aim was to see the points where your derivative is 0. This one is never 0, right? This function's derivatives are never 0. That means your focus should now be on sin x. On the other branch, this one. This is going to give you the derivative equals to 0. So the other branch is sin x for x greater than 3. Sin x. So it includes cos x. You have to find where cos x is 0. But the other condition is that x should be greater than 3. So two conditions on x. First is cos x should be 0 because this is the derivative of sin x. That's what we're trying to find, where the derivative is 0. And the other condition is that it should be greater than 3, right? Because only there your function is sin x. Everywhere else your function is mod x. So you'll have to make sure that your x is greater than 3. So cos x is 0. When is cos x 0? At x equals to, in general, it's 0 at x equals to pi by 2. 3 pi by 2 and all of those. But your pi by 2 is, pi is 3.14. And if you divide it by 2, it's definitely less than 3. That means you can't include this point. So this point is excluded. Then you can come to 3 pi by 2. 3 pi by 2 is greater than 3. And every other consequent term here, 5 pi by 2 and all of these are also greater than 3. And when we take the odd multiples of pi by 2, we also take minus 3 pi by 2, minus 5 pi by 2. I forgot to mention those here. Here. Plus, minus, plus, minus. This is plus pi by 2. Minus pi by 2 is also a point where your cos x is 0, right? But here you can't take these points for the same reason, because they're all less than 3, right? We want x greater than 3. These all are negative numbers, obviously less than 3. So you can't take these points either. Is this okay to everyone?
Yes, ma'am. Got it, ma'am.
You can only take x equals to 3 pi by 2, then 5 pi by 2, then 7 pi by 2, and keep going on like this. That's it. Which is going to give you these points as critical points. So graphically, your critical points are these. This. This is also a critical point. This is also a critical point. We obviously can't mark all of them. They keep going on. So your critical points now are 0, 3, 3 pi by 2, 5 pi by 2, and they keep going on like this. Is that okay?
Yeah.
Yes.
Okay. Now let's classify your critical points. Your critical points are further classified into 3 points. So one is local maxima. The other is local minima. So if there's a critical point, then either it's a local maxima or it's a local minima, or there's also a possibility that it's neither of them, right? So if it's neither of them, like in this case, let's say, do we have, okay, we don't have an example of neither of them. We have these critical points, right? What is this? Can you classify this one? Is it a local maxima, local minima?
This is that is a local minima, 0.
This is the local minima. What about this one? 3. And then this one. Let's do
is
only
the
these two.
critical point here.
This is a local maxima.
Yeah.
Obviously, it's a critical point, but it's a local maxima too.
Yeah.
Or actually, just 1 second, because you have your graph here too, right? and your value at 3 is this. At 3, you have defined your function to be mod x. That means the value at 3 is this. This is the
That is
value at 3.
a local maxima.
So this is a local maxima. What about this one? This is a local minima. And similarly, all of them are either a local maxima. So this is an example where every critical point is either a local maxima or a local minima, but that's not always the case. So critical points are either local maxima, local minima, and it's also possible that it's neither of them. And then you call it a saddle point. So let's see an example of that too. Let's take example of saddle point. Let's take x to the power 4, or not even x to the power 4. Let's take x cube for simple. X to the power 4 is not an example of this. Let's take x cube. Graphically, if you look at it, it looks like this. So this can't be a local maxima. We've already discussed this. And this is not a local minima either. That means it's a saddle point. But what was our condition? If we go by the definition, we say, first we have to make sure what's a saddle point. A saddle point is a critical point which is neither a maxima nor a minima, right?
Yeah, right.
So that's your critical point. Now, if you have x cube, let's go by the definition. You want points where either x cube is not differentiable or the derivative is 0, right? So is there any point where x cube is not, what's the derivative of x cube?
3x square.
Yeah, and it's for all x, right? The derivative is 3x square for all x belonging to real numbers. That means it's differentiable everywhere. That's why its derivative exists everywhere. That means the one case is done, that you don't have any point where it's not differentiable. Other part is where your derivative is 0. So equate this equals to 0. You will have x equals to 0. That means your critical point is x equals to 0. This is your critical point for this function. Now to check if it's a local maxima or a local minima or it's neither, then it would mean that it's a saddle point, right? So your x cube looks like this. Or your x cube is an increasing function. Even if you don't know how your function looks like, you should know that the graph of x cube looks like this. You would at least know that x cube is an increasing function, right? And if you have an increasing function on the entire real line, can it have a local maxima or local minima? The domain is the entire real line. And this is, let's say this is an increasing function. Can it have a local maxima or local minima?
I don't think it has local maximum. If it is increasing, then
Definition says you need an interval. If this were a local maxima or a local minima or any other point, then you need an interval around that point where this should have maximum or minimum. Now this is neither the maximum because there are values less than this. These are less than this, right?
this is the
And these
saddle
are
point,
greater than
right?
this. Yeah. So not this one. It's a saddle point here in x cube. What I was trying to say here is if you have an increasing function on the entire domain real numbers, if your domain is real numbers and your function is increasing, then it cannot have a local maxima or a local minima because it keeps increasing. For a local maxima or a local minima, you need one interval where you can have a maximum value around that point. That's not possible in the case of an increasing or decreasing function. So your x cube does not have no local maxima or minima. Now what does this imply? X equals to 0 is a critical point, but x cube does not have a local maxima or local minima. or you can see it from here. X equals to 0 is not a local maxima, not a local minima. That means it has to be a saddle point. Is this fine? Now, how do you check?
Got it.
This is like a very rough method to do things, right? So we need to have like a test. So we have a test called second derivative test to identify local maximas or minimas, which says, let's say you have a critical point and you have to find if it's a local maxima or it's a local minima. Then what do? First thing is, if your f dash, let's say if your f dash a is 0, then to identify as local maxima or minima, we have this test, second derivative test, which says that if the double derivative at a is greater than 0, it's local minima. And if the double derivative at a is less than 0, then it's local maxima. For example, let's take x squared. Or let's take sin x. Sin x is like a perfect example which fits everywhere. And we know that pi by 2 is a critical point of this, right? Pi by 2, 3 pi by 2, in fact, plus minus both. These all are critical points, right, for sin x. So if you have to identify whether pi by 2 is a local maxima or a local minima, what you do is, first you find the derivative. So we already have found the critical point, so you don't have to go to derivative. You can directly come to second derivative. What's the second derivative of sin x? First derivative is cos x. And then the derivative of cos x is minus sin x, right? So it's minus sin x. What was the next step? You have to put these points for x equals to pi by 2. The derivative, if this is your function. So what do you have to find? F double dash at pi by 2. If the double derivative of f at pi by 2 is greater than 0, then it's a local minima. If it's less than 0, then it's a local maxima, right? What is f double dash of pi by 2? F double dash is minus sin x. If you substitute pi by 2 in this function, you will get minus of sin pi by 2, which is minus 1, which is negative. Now this means pi by 2, what is it? Is it a maxima or a minima? This says if f double dash is greater than 0, it's local minima. If it's less than 0, it's local maxima. This one is less than 0. And you can check it from the graph too. We checked it from the graph, right? Where's the sine graph? Sine curves. Here. Pi by 2 is a local maxima here. And for 3 pi by 2, if I'll substitute 3 pi by 2, f double dash for x equals to 3 pi by 2, f double dash at 3 pi by 2 is minus sine at 3 pi by 2, which is minus of minus 1. 1, which is greater than 0. This means your 3 pi by 2 is local minima. Is this okay? Now there's a third
Yes,
case
ma'am.
where what if your f double dash a is 0? What if this happens? Now if this happens, that means your test is inconclusive. Test inconclusive means you can't say. You will have to resort to some other approach to find if it's a local maxima or it's a local minima or it's a saddle point. This test is not enough to find that. That's what test inconclusive means. Is that okay? And then we have global maxima. Just 1 second. Then we have global maxima and minima. So global maxima and minima are these ones. Let's say if you have this curve, then we just saw that these were local maximas. This one, then this one too, and this one too. These were local maximas, and these were local minimas. This you can consider not this one if it's going down, or you can take this one. This one, the end point, then this one, this one, this one, this one, and let's do this. If it's this, then this point. So the blue ones are local maximas. The white ones are local, the white ones are local maximas. The blue ones are local minimas. And out of these, the global maxima is the one with where the maximum of the function is attained. So if you're back, because the function's maximum is attained, and global maxima is unique. Local maximas could be 2, 3, or infinite, but global maxima is unique. So this will be your global maxima, right? Because your function's maximum is attained here. And what will be the global minima? This will be the global minima. So this point now, this one is a local maxima and a global maxima both. It's both. And this one is a local minima and a global minima both. That's your definition for global maxima and minima. Now let's come to areas. How do you find the areas and Riemann sum and all? So let's start with Riemann sums. Let's say you have this function and you have to find that Riemann sum is basically, there are some things given to you for Riemann sum. The first thing given to you is, what do you need to find the Riemann sum? First is your function, right? You need a function. Then second is the interval. Third is, all of these will be given to you in the question. Third is the partition of interval. Fourth is one point from each, one fixed point. From each interval or from each partition interval. What do all these things mean? So your Riemann sum is basically, let's say you have to find the area under this curve. And how do you do it? One simple way is, let's say this is where your function is defined. One simple way is you draw rectangles here. So if you take this and you're drawing the rectangle, let's say if you're taking this thing and you're taking the height to be this, let's say, then this is one rectangle. And the next one you're taking is, let's say, this one. And let's say your height is, because you can only, this is not, if you take this is not a rectangle, right? So for this to be a rectangle, you need a fixed height from here to here. Let's take that fixed height to be this one. Now let's take this interval and the height, let's take the height to be this. the same height as previous one. Then the area, if you do the same here each time, if this is the rectangle, then this is the rectangle, this is the rectangle. If you try to estimate the area using rectangles, this is just estimation. Obviously, this is not the exact area. Then your area will be this. Your exact area is this. Obviously, which is under this curve. This is your exact area. What you will get from these rectangles would be this. This area you will get, then this area you will get from this rectangle, and this area you will get from this rectangle. And if you'll add the areas of all these rectangles, you will get the green area, right? So this gives you a rough estimate of the area here, a very rough estimate. And if you will keep increasing these partitions, these are called partitions of your interval. Let's say this interval is A to B. And these are called partitions. That means if this is A, then x0 is equals to A. Next point taken to be x1, then x2. This collection is called partition. Let's do it with an example, because without that, it will all be vague. So let's take this example. Let's say you have to find the Riemann sum of. So in Riemann sum, what you do is Riemann sum of fx on interval, let's say AB, with partitions. So partition is of this interval. Partition means that if this is the interval AB, or in particular, let's take 0 to 1, then the partition could be this: 0 to 0.1, 0.2, 0.3, and then this 0.9, and then finally this 1.0, right? This could be one partition, or you can take some other partition, which could be 0, half, and then directly 1. So your partition from here is 0, 0.1, 0.2, 0.9, and 1. This partition is 0, half, 1. If you have something like this, 0 to 1, or let's say you have 0 to 4 here, 5, then this could be 0 to 2, 2 to 3, then 3 to directly 5. The partition would be 0, 2, 3, 5. If you instead you do this 0, 2, 4, 5, then the partition will be 0, 2, 4, 5. I hope what partition means is clear to everyone. So this is partition. Partition means you're dividing your interval into some parts, and then you're writing these parts as this. So let's say your partition is x0, x1, and so on till xn. What else do we need? We need fx, interval, partition, and a fixed point from each interval, which means this, each subinterval. So if this is a subinterval of your partition, this is the partition, right? 0 to 0.1, then 0.1 to 0.2. This is the partition. Then you have to take one point from 0 to 0.1. Take some point, and that point will be given to you in the question. So let's call this one x1 star. Let's call this 2 x2 star. This one x3 star. This will be x9 star, and this will be x10 star. So you have to choose one point, one fixed point from each partition of the each partitioned interval. The partitioned interval are these. You have to find one. You don't have to find it. It will be given in the question. So this is what you require to find the Riemann sum. What does it mean? Basically, when you have a function, let's say this is the function, you have an interval AB, and you have an interval 2. This is, let's say, x0, this is x1. You have a partition 2, x2, x3, and let's say this is x. Then your partition is x0, x1, x2, x3, x4. Function is this, let's say, and interval is AB, right? And let's say the point given to you, it doesn't have to be in the middle, it could be any point. It could be this one. For this subinterval, let's take this point. For this subinterval, let's take this point. All of these things are given to you in the question. You don't have to choose these things. x1 star, x2 star. Let's take this one, x3 star and x4 star. So your Riemann sum, what it does is, take this thing as this. So take the width of the rectangle as this and take the length as this, as the height at this point. So if you've chosen x1 star to be this point, take the height at this point. The height is this, right? What is this height? If this point is x1 star, then what is this height?
Y-intercept.
Y-intercept. How is this y? If you have if you have this graph, and I'm asking you what this height is. If this point is A, let's say this point is A, this function is gx, then what is this height?
GA.
Right, GA. So if this point is x1 star, then this height should be f of
Fx.
x1 star, right?
Yes.
This is that height, fx1 star. So if I draw a rectangle here with breadth this is the breadth from A to x1, this is breadth, and this is the height. I'm choosing this to be the height. Here the height is varying, right? At this point, the height is something else. At this point, it's something else. At this point, it's something else. In this entire interval, the height is varying. I'm taking it to be constant as fx1 star, as the height here. So it will be this, right? Then there'll be a rectangle with width this, breadth this, A to x1, and height as fx1 star. This, right? This is a rectangle where what is this? x1 minus A, right? This length is the x1 minus A, and this height is fx1 star. What's the area of this rectangle? This rectangle.
Fx1 star multiplied by x1 minus A.
Right. So this is the area of this rectangle. Now let's come to the next subpartition, which is this, right? x1 to x2. And we do the same thing here. x2 star is the point that's given in the question. So if you, let's take this height then. This height was fx1 star for this entire rectangle. For the second rectangle, we're taking the height to be this one. This is why this point is given, for you to fix the height. So this height is fx2 star. Fix this height for this entire interval. So it will be this interval, and the height is just this. So the rectangle would be this one, right? The next rectangle is this. And what's the area of this next rectangle? This distance is x2 minus
How
x1.
we calculate breadth here? The breadth of the rectangle. Breadth of the rectangle.
This is the breadth, right?
Okay.
This thing. What do you think is the length of this? If you have x1 here, x2 here, then what's the length of this? It's x2 minus
x2
x1.
minus
Right?
x1, yeah.
That's what we're doing here. So this is x2 minus x1. And for the rectangle, because the height keeps varying on this curve, so we have fixed the height to be x1 star. So the height is fx1 star. So this thing is fx1 star. This thing is x2 minus x1. And what should be the area?
Area of fx into
X2 minus X1.
x2
Right.
minus x1.
Now, so far we have covered this area. and then this area. And we keep doing for all of these. We do the same for this one. So this is your breadth. The height is this. So it becomes this. And your area becomes this. Same goes for this one. Your height is this. And your area becomes this. Right? So your total area that you've added here, fx2 star, x3 minus x2 plus fx3 star, x4 minus x3. This is the area that's marked red, right? Under these rectangles taken together. One more thing, this, if I change these partitions, now I've taken this x1 from A to B, I've taken x1, x2, x3, and then x4. So I've taken only 4 points in the partition. If I'll increase the number of points, do you think it will be a better approximation? The area under these rectangles is not the exact area under the curve, right? It's just the approximation. Please turn off your mic. So this area, the red marked area, is the rough estimation of the area under this curve. If this is your curve, the area under this curve is this, the one marked in green, right? This will be the area under green curve. So if you have to find the green area, which is under the curve, the original fx curve, you can try to estimate it using rectangles, right? That's what we have done. If you have only 3 points in the partition, x1, x2, x3, then your area will be something like this. Now, if you'll increase the number of points, if I'll increase it to this, let's say instead of x1, I'm taking 6 points this time, x1 to x6. This is A, this is B. x1, x2, x3, x4, x5. And you're taking the same curve, this same curve. Then wouldn't it give you a better approximation? Each time you'll increase the number of partitions here. And then you will take the rectangles. You will get closer to the curve, right? If I'll increase it even more, if I'll take it this, if I'll take these to be the partition, then my rectangle would be this. This one, and this. Then this one, and this. Only very little area would be redundant, right? This area is the redundant one, right? So if you increase the number, can you see if we increase the number of partitions, you keep coming closer to the exact area under this curve? Is this clear?
Yeah, this is clear now, but why we require this area of that graph and the curve?
This is simply a way to find the area under a given curve. And Riemann sum, by the way, does not give you the exact area. It just gives you the approximation. If you'll increase the number of partitions, if you'll increase this, then your area will become closer. Also, okay, let's not get into the theoretical part because you don't need to do that. So this is called the Riemann sum. You only need to know that if I change the partition, if I change this partition, would the area also change? Let's take a very simple example.
No, the area would not change.
Not the area under the curve. I'm talking about the area under the rectangles.
Yeah, area
Let's
under the
see it
rectangles
clearly.
will obviously change if we change the partition. But the area
If
of
you
that
have
curve or the
this.
graph would not.
Okay, let's say this is 1 to 10. If I have two partitions, or let's say if I have this partition 5 to 10, and then the other I'm taking is this one 1 to 10, and this time I'm taking 2. So 1 to 2 and then 2 to 10 for the same curve. So if I'll take this and I'll take the middle point to be this, or the point that we take x1 star and all. So if this is that point and this is the other point, then the area would be this, right? This is the height that you have to take, this one. So this will be the first rectangle and this will be the second rectangle, right? Height you're taking to be this. So now the area will be this, under this rectangle and then under the second rectangle. Now if you do the same thing here, let's take the point to be this here and this here. Then the height is this. And here the height is this. This one. So it's this. And this area under these two rectangles is different from this one, right? This marked area is different from this one. So if you change the partition, even if you don't increase the number of partitions there, even if you don't increase the numbers here, you just change the numbers, then also your area is going to change. If you increase the number, then also your area will change. If you will change the function, then also your area will change. So it depends on these four things. Your function, the interval. If I'll change the interval from 0 to 1 to something else, or from 0 to 10, 1 to 10 to 2 to 10, then the area will obviously change, right? So fx, it changes. If fx changes, interval changes, partition changes, or the fixed point changes. Even if you change this point, instead of this point, if you take this point, then your rectangle would be, instead of this big rectangle, you will have this rectangle. A smaller rectangle. Then also your area under the rectangles is going to change. And area under these rectangles is your Riemann sum. This is your Riemann sum. So for Riemann sum, you need four things. And this is the Riemann sum. So your Riemann sum, the formula for Riemann sum is given by, general formula is f x I star xi minus 1 or xi minus 1, I varying from 1 to n, where n is the number of partitions. If you've taken x0, x1 till xn, then this is that n. If this is k, then this will be k. So this is your Riemann sum, where fx is the required function. Interval is, let's say, AB. Partition is x0, x1, and xk. And the points, these points are x1 star, x2 star, and so on. Xk star. Is this okay? Shall we do one example?
Yes, please.
Okay. Just give me 1 minute. Okay, so let's do this example. Let's do this. 3x plus 1. Let's say this is your function. And let's say your interval is 0 to 2. And partition is 0, 2 by n. And I forgot to mention one thing, which is if you will take okay, let me just erase this thing and so your Riemann sum is this, right? Riemann sum for a function is f x I star xi minus 1, I varying from 1 to n. Now let's say you take this thing. Now this is called mesh of your partition. If this is your partition, for example, let's say your partition is this. Let's do it with an example because definitions are getting really messy. So 0, 1, 2, 5, 7. Let's say this is the partition of an interval from 0 to 7. Then the mesh of this partition is basically the largest length of the subinterval. So subintervals are 0 to 1, 1 to 2, 2 to 5, and then 5 to 7. Which one has the largest length? What will be the mesh of this partition? Mesh of this partition is this length is 1, this length is again 1, this length is 3, this length is 2. The maximum length is this one, right? 2 to 5. So the mesh of this one, if this is your partition P1, then the mesh of P1 is 3. Now, if I'll take the mesh of this partition, this thing, tending to 0, that means every interval's length squeezes here. Then this becomes Riemann integral, or in simple words, your definite integral, which is denoted by this, fx from a to b. So let's say you had an example here, right? Your example was 3x plus 1. This was your function. This was the partition. Your interval was from 0 to 2. This was 2 by n, 4 by n, 6 by n. Let's take this to be the partition. Going till 2n by n, which is just 2. Right? And what else do we need? To find Riemann sum, we need a function. We need interval and partition. What else do we need? We need a point here, right? Which we call x1 star, x2 star. We need these points too. So in this particular example that we're doing, the points are given to be this. So for this interval, x1 star given is this 2 by n. For this interval, x2 star is given to be this point. For the next one, 6 by n, 4 by n to 6 by n. The point given is 6 by n. So your x1 star is 2 by n. x2 star is 4 by n. x3 star is 6 by n, and so on, so on. What will be the last point? Obviously, we're choosing this one, right? So if this is the last interval, we'll be choosing this point. The left end point, right?
2.
Left end point from each set, from each interval. So the last point will be 2. And what would it be? Xn star, right? So what should be the Riemann sum then? How do we find the Riemann sum? The formula is f x1 star x1 minus x0 plus fx2 star x2 minus x1 and so on, so on, till the last one, right? It doesn't keep going on, it stops there, stops at a point. So this will be, what's your x1 star? It's 2 by n. It's f of 2 by n. What is
Isn't
x1
it
minus x
that
naught? Yeah,
is the area of that curve, right?
it's not the area of this
That
curve.
that's
It's
the
the
Riemann
Riemann
sum.
sum.
You have to,
Riemann sum
yeah.
is different from area.
We
Riemann
have
sum is
taken that
yeah.
the area of the partition that led into bread formula, area the area of the rectangle,
Yeah,
and we have just doing sum of that all rectangles.
yes, that's it. That's your Riemann sum. And it's different from the area under the curve. It's not the same as the area. But if you want to find the area, where have I written that thing? Yeah. If you want to find the area, you can take the mesh of your partition tending to 0. That means if you take your partitions to be very small, now we are taking partitions to be very large, right? We're taking the partitions to be these. These are too large. If you take the partitions to be too small like this, where the length of these partitions, these things is approaching to 0, that means it's almost 0, then that will give you the exact area. That's why we either write the exact area under the curve as this, or you can write it as summation fxi star xi minus 1, I varying from 1 to n, and n tending to infinity. That by n tending to infinity, I mean that you're increasing the number of partitions. Let's say here you have 2 partitions, then you do 4 partitions, then you do this number of partitions, and you keep increasing them. So your area under the rectangles becomes closer to the exact area under the curves. And if you'll take the number of partitions, these things. If you'll take the number of sub-intervals tending to infinity, then you will get the exact area. That's what we are going to do here. We'll take n tend to infinity. So fx1 star is f2 by n, x1 minus x naught. What's the length of this one? This is 2 by n. Length of this is also 2 by n. Length of this is also 2 by n. So they all have a common length 2 by n, right? So this length is 2 by n. This length is also 2 by n. What is fx2 star? X2 star is 4 by n. Fx2 star then will be f of 4 by n. Next will be f of 6 by n multiplied with 2 by n. So on till f of 2 and 2 by n. Is this fine? As a Riemann sum?
Yes.
Okay. What is f of 2 by n? So your function is this, 3x plus 1. If you substitute 2 by n here, you'll get 2 by n plus 1 plus, let's take 2 by n common from everywhere. Because we have 2 by n here, 2 by n here, and basically 2 by n in every term, right? So you can take 2 by n common. You'll only be left with f of 2 by n plus f of 4 by n plus so on till f of 2, right? This is equals to 2 by n. F of 2 by n is 3 times 2 by n plus 1, 3 times 4 by n plus 1. This will be 3 times 2 plus. You can write this 2 as, because as in partition, it's just 2n by n, right? Remember, we wrote it like this, 2n by n. Plus 1. How do you add these? So this has a 1, and how many terms are there? So we start with 1 term, 2nd term, 3rd term, and we have n terms like this, right? we have in total, this is the first one, 2 into 1. This is first one. This is 2 into 2. 4 is just 2 into 2. So this is the second term. This is the nth term, right? So how many ones are there? Can you count the number of ones from here? This is first one, then second one, then so on, so on. This is the nth one, right? So 1 plus 1 plus 1, this is 1 plus 1 plus 1, n times. And then you have 3 times 2 by n plus 3 times 4 by n, but we have taken 3 common, so you can just simply write 4 by n. Then this is n. 6 by n, 3 times 6 by n, so on till 3 times 2 by n, 2n by n, right? We have taken 3 common from all of these ones. This one, this one, this one, and this is what we get. Is this much okay? Does anyone have a doubt so far? So this is going to give you 2 by n. This is 1 added n times is going to give you n. And this will be 3 times. Let's take 2 common from all of these. So you'll have 3 times 2. 1 by n plus 2 by n plus 3 by n plus n by n. Or actually, you can take 2 by n common. You can take n common too, right? So you will have n here. What's the sum of first n natural numbers? I think it's n plus 1. Is it n plus 1 by 2? Or? Please mute yourself. Yeah, it's this, right? n plus 1 by 2. So this sum is from 1 to n. The sum is n plus 1 by 2. So this becomes 2 by n plus 6 by n from here. And this is just n plus 1 by 2. So this will be 2 plus this is 12 by n square. And we have an n here. Okay, let me just write this down. This becomes 2 plus 6 by n plus 1, right? And this is the same as 2, 6, 1 plus 1 by n. So this is when n tends to infinity, what happens to this? Now this is Riemann's sum. And if I'll take n tending to infinity for definite integral, or you can say for the exact area under that curve, then this will be 2 plus 6. Because if n tends to infinity, this goes to 0, right? Which is 8. Is this okay?
Yeah,
Yes.
okay.
Okay. Shall we do one more example, or is this enough?
Yeah, it
Let's
will
do
be
one more.
good if we can see another example.
Okay. Let's first get done because we're left with very little time. Let's first get done with the rest of the syllabus, and then we'll come to the example. Is you can give this one a try if you want to. X square plus half. Take the interval to be 0 to 4 and 4 subintervals. The partition is 4 subintervals of this. So what 4 equal subintervals? What will be the 4 equal subintervals from 0 to 4? So the partition is basically 0, 1, 2, 3, and 4. Is that okay? So this is your partition, this is the interval, and this is the function. And the points that you have to take are, let's first discuss this thing. You have to take, so this is your interval, you've been asked to take these ones.
Ma'am, you have said that we have to take 4 equal subinterval, right?
Yeah, these are
The
equal,
point-
right? One first
The
subinterval,
point
second
you have
subinterval.
mentioned is okay.
4 equal subintervals, not the points in partition. Points are 5 in partition, but the subintervals are 4, right? This is first, this is second, this is third, and this is fourth. So and what else do we require to find the Riemann sum? We need one more thing, right? We have a partition, we have the interval, we have the function too. What else do we need? We need xi stars, right?
Yeah,
The
but
formula is summation of fxi star. So we need these points too. All of these things will be given in the question. So if it's given to you in the question, first is, if it's given that you have to take the left end point of each interval, this one. Left end point for each subinterval is this. Left end point is this. For first subinterval, for second subinterval, the left end point is this. For third subinterval, the left end point is this. And for the fourth one, it's this. Then it's called left Riemann sum. That means this will be equal to summation f x. What will be if this function is, if the function you're taking is f, then what will be the left Riemann sum then? F of 1. The lengths are just 1, right? The length of the interval is just 1. 0 to 1 is 1. 1 to 2 is also 1. This is 1. Then you have to take the left end point of this second subinterval, which is 2. Left end point for left Riemann sum. F of 2, length is 1. F of 3, length is 1. And then F of 4, length is 1. Is this clear? So the left Riemann sum then will be this. Similarly, you can find right Riemann sum. What will that be? In this case, we were taking the left end points of each interval. Now we'll take the right ones. This one. Take the right end point for this interval. So if you have from 0 to 1 to 2, 3 and 4. So for this interval, take this point. For the second interval, take this point. Third one, take this one. Fourth one, take this one. So your right Riemann sum becomes f of 0. Length of the interval is 1. F of 1, length is again 1. F of 2, length is 1. F of 3, length is 1. And finally, we have middle Riemann sum. So for middle Riemann sum, you have to take the middle point of each subinterval. So if this is 0, 1, 2, 3, and 4, then the points you have to take is, for this interval, take 0.5. For this interval, take 1.5. For this one, take 2.5. For this one, take 3.5. How do you find the middle point? If you have this subinterval, let's say x0 to x1, then to find the middle point, you just have to do x1 plus x0 by 2. In this particular example, it's very easy. But let's say if you've been given from 4 and then it is 8, and it's 8 plus 4, 12, and then divided by 2. So the middle point here would be 6. So the middle Riemann sum becomes f of 0.5. This is x1 star. The length is 1. F of 1.5. The length is again 1. F of 2.5. Length 1. f of 3.5, length 1. Is this clear? Try to find all of these three Riemann sums for this function and this interval. Can you guys do this? Okay, then coming to antiderivatives. So you've already done derivatives, right? You denote it by this. Let's say you have a function fx, then its derivative is noted by f dash x. Let's call it fx, capital Fx, right? For example, let's say you have sin x, then the derivative of sin x is cos x. Let's call this cos x as fx and this sin x as small fx, right? So if your f dash x is capital Fx, and we'll take the opposite of this. Let's say we say that the derivative of this, how do we say it? Derivative of small fx is capital Fx, right? But what? So capital Fx is derivative of small fx, and small fx is antiderivative of capital Fx. So you can just say fx plus c. Here you can say fx plus c is this. And we denote it by antiderivative of capital Fx denoted by this thing. Also called the indefinite integral. This is called the indefinite integral or the antiderivative. Both are correct. So let's say you have been given, let's take one example. Let's say you have x cubed plus x squared plus 6x to the power 7 plus 0.99x. And you have to find the antiderivative of this. Then what is it? So let's go term by term. Let's go by this term first. What do you have to find? You basically have to find a function whose derivative is x cubed. So if I have x to the power 4, what's the derivative of x to the power 4? It's 4x cubed, right? But I want x cubed. That means I should divide it by 4 or divide this by 4. So the derivative of x to the power 4 is 4x cubed. What's the derivative of x to the power 4 by 4? What is the derivative of this? It's this, right? Yes. So that means you can just simply take, we anyway have this identity too for integrals. So this will be x to the power 4 by 4. This will be x cubed by 3. This will be 6x to the power 8 by 8 plus 0.99 x square by 2. So this is capital Fx and this is small fx. This is antiderivative of small fx and this is the derivative of this. If you will take the derivative of this, you will get this. If you will take the integral of this, you will get this. They are the reverse of each other. Like sin x, the derivative of sin x is cos x. So the antiderivative of cos x is sin x. That's it. Let's write some definite integrals of, let's first write some integrals to remember that you need to learn. So let's start with 1. We're writing the antiderivatives here. And this is the function. So what's the antiderivative of 1? It is x. Antiderivative of x to the power r is x to the power r plus 1 by r plus 1. That's what we did here. X cube, then x to the power 3 plus 1 divided by 3 plus 1. We use this thing. Then we have cos x. For cos x, you have minus sin x. The antiderivative of cos x is minus sin x. For sin x, it's cos x. So, see, x is antiderivative of 1 and 1 is the derivative of x. Similarly, this thing. This is antiderivative of x to the power r and x to the power r is derivative of this thing. For tan x, the antiderivative is secant square x. For secant x, your antiderivative is secant x tan x. Sorry, we're writing the, okay. Secant square x is the derivative for tan x, right? So the antiderivative for tan x is natural log of secant x. And the antiderivative for secant x is natural log of secant x plus tan x. For cosecant x, yeah.
Also for the cos x, the derivative is minus sin x, right? Or sin
Yeah,
x.
1 second. I think I've written for cos x, your antiderivative is sin x, and for sin x, your antiderivative is minus cos x. I had written the derivatives there initially. I didn't realize. So cos x is sin x is the antiderivative of cos x, and cos x is the derivative of sin x. Then for cosecant x, it's also a constant is needed everywhere. Plus constant, plus constant, plus constant. So if you're not taking definite integrals, if you're taking just integrals, you're supposed to add constants too. Just add the constant at the end. I'm not writing it everywhere, but it's needed. Then, do we have any other important functions? We have the exponential functions, e to the power x, it's e to the power x. And for e to the power lambda x, it's, okay, we don't need this. This comes under this one. For e to the power lambda x, you will have e to the power lambda x by lambda. For natural log of x, you have one by x. A to the power x we missed, right? For a to the power lambda x, you will have a to the power lambda x, the same as e to the power lambda x, with only a minor difference, a to the power lambda x by lambda, and you will have a natural log of a here. I think that's it. That's what you need to do the antiderivatives and all.
For
These are
the
the basic.
log x, the derivative is 1 by
Yeah.
x.
Log of x is left, right? For log of x, you will have 1 by x, and then you will have so if it depends on the base. If you have 10 here, I'm assuming you're talking about base 10. Like here you have base e, right? Natural log ln means log base e. Then your antiderivative is 1 by x. But if you have base 10, then you will have natural log of 10 here. Are we left with anything else? This is it, right? I don't think you need any other function. That's all you need. So, yeah. Then I think next up we have some properties of definite integrals. So properties of definite integrals are the first property is on the sum f plus g. Let's say it's from definite integrals are when you have a value f from a to b. When you don't have it, then it's indefinite integral. In simple words. So if you have this function, then dx in proper terms. If you have this, then this can be written as fx dx. And I'm not writing dx everywhere, but you have to. This is it. I'm skipping it from here too. Then if you have minus here, then you will have minus here. So if it's a plus, you will have plus here. If it's a minus, you will have minus here. And let's say you have, and one is of scalar one, right? Let's say you have, let me include this one here too. So if you have CF here, CF plus minus G, then this becomes C, or you can just have this C here. First it becomes this, and then you can take this C common. So it will just be this. And this plus minus is basically, if you have a minus here in between CF and G, then you should have a minus here. If it's a plus, then you should have a plus here. This is one property. Then the other one is if you change these two, AB, F is the same as F integral from B to A, but a negative sign gets added here. So if you interchange these two, a negative sign will be introduced. And then the third one is this splitting one. Let's say your C lies between A and B. If there's a number between A and B, then this thing will become integral. Instead of taking the integral from A to B, you can take the integral from A to C and then take it from C to B. If you take from A to A, this is just 0. And this one's not required, but if you want to know, if you have something like this, if you have the integration of some mod function from A to B, and if this turns out to be 0, this means your mod of fx is also, this is not required. You don't need to know this thing. Leave this. And then the fifth one is if your fx is greater than gx, for all x belonging to domain, or for all x belonging to domain except for some finite x. If except for some finite number of elements in the domain, your fx is always greater than gx, then this implies the integral of fx from a point A to B will be greater than integral of gx from A to B, or you can write it on domain. The integral of fx on the domain will be greater than or equals to the integral of gx on the domain. We're assuming that the domain of both of these are same. Is this okay? So these are more or less all the properties for definite integral. Yeah, and then we're left with integration by parts. So for integration by parts is basically used when you have two functions. Let's say you have product of sin x and cos x. There are other ways to do this. Someone who's done integration and all would know this, but you can also do it by integration by parts. If you have two functions in multiplication under integration, let's say you have ux multiplied with vx. Then this is the same as integration of, okay, ux taken as it is, integration of vx, and then subtract derivative of ux and integration of vx. So what we're doing here is, in this term, what we're doing is, first we're taking the integral of vx, then we're multiplying this integral with the derivative of ux, and we're taking the integral of this entire thing again. Which means, let us do one example on this. Let's say you have x cos x and the integral of this one. And we have a rule, an isolate rule for it. Isolate rule means, suppose you're applying this rule, integration by parts, then you should know which function is, if this is x cos x, then which one should I take ux and which one should I take vx, because it's going to make difference, right? If I'll take this as ux, I'll get something. I won't get the same things. I might get the ultimate answer same, but I'm not going to get it same, right? So how do we change how do we choose which function to take ux and which function to take vx? So your priority for ux should be determined by this isolate rule, which is, first choose the inverse. If there is an inverse trigonometric function, choose that to be ux. So let's say this is inverse trigonometric functions, this is logarithmic functions, this is algebraic functions, this is for trigonometric functions, and this is for exponential functions, e to the power x, a to the power x, all of those, e. That means, let's say you have a to the power x and cos x. Then which one should I choose as x, as u function? As this one. So by this isolate rule, you should be choosing ax is exponential function, cos x is trigonometric function. That means you should choose this as ux function and this as vx function, and then apply this rule, right? Similarly, you have x and cos x. So cos x is trigonometric function t, x is your algebraic function a. That means you should choose this as u, this as v. Now let's apply the isolate rule. So you'll have x as it is, then integration of cos x, then derivative of u function, which is x. That means derivative of x. And then the integral of v function, which is cos x dx. And this entire thing under dx. Now this expression, this one, simplifies to x, and the integral is sin x, right? So yeah, this, and then for this one, the derivative of x is 1. The integral of cos x is this term, integral of cos x. Integral of cos x is sin x. And then dx, this one. So this will be x sin x minus integral of sin x. So integral of sin x is minus of cos x. So this will be x sin x plus cos x. This is it. This is your Eilert rule. Sorry, the integration by parts. And then we have the last thing, which is the substitution. Substitution is basically to solve integrals. You can use substitution method, which is, let's say you have something like the integral of f of gx, and here you have the derivative of this function g dash x dx. And what you can do is you can substitute this entire thing, and let's say your limits are a and b. So you can substitute this, the argument of f as t. If I substitute gx is equals to t, then this will become f of t. G dash x will be, what we do here is d gx by dx, right? This will be dt by dx. This is g dash x. That means your g dash x is equals to dt by dx, or in other words, you can say your dx, g times x should be equals to dt. That means you can replace this entire thing with dt. So if you substitute gx as t, your g dash x dx will be dt. So this entire thing will become ft dt, and these limits will also change. So when you had g here in the argument, your limits were a to b. Now you have t. For gx, you took a to b. If you will replace this with a t, you should take ga and gb. So this entire thing becomes ga, gb. This integral gets simplified into this one. Now you can solve this. Let's do one example. Let's say you have 3x square root of x square minus 5. What you can do is dx. Substitute x square minus 5 as t. Now if you substitute x square minus 5 as t, your 2x derivative of this will be dt by dx, derivative of this with respect to x, derivative of this with respect to x. That means your 2 times x dx will be equals to dt. But we have 3 times x dx, right? So what you can do is take 3 here, x, and this thing here. Square root of x square minus 5 x dx. Then multiply 2 here and divide this thing by 2 so that everything remains balanced. Now 2x dx is dt. 3 remains as it is. 2 remains as it is. This is t dt. This is t. So this becomes root t. This is this. Now this integral, this one, gets transformed into this one, which is the same as 3 by 2 integral of t to the power half dt. And how do we find the integral of this? This is t half plus 1 by half plus 1, 3 by 2. So this is 3 by 2, t to the power 3 by 2 and 3 by 2. These two get cancelled. So you will be left with t to the power 3 by 2. And t was nothing but, we substitute because obviously we started with everything in x. So we want the answer in terms of x. So we substitute back the value of t from here. So your t was x square minus 5. So this becomes x square minus 5 to the power 3 by 2. And we're done. I think we're done, more or less done with the syllabus for week 9. If anyone has any doubts, you can ask. Else we can end this session here. Does anyone have any doubt?
Hello, ma'am.
Yes.
Ma'am, I have a doubt in quiz paper. So, can you discuss that? I mean, not a doubt, but I have found something error in the question.
Okay, which question?
Question number 7, ma'am.
Which set did you have? Can you just
Ma'am,
can you
I
tell me the
don't know.
question?
Okay.
Just 1 second. Let
Yes,
me
ma'am.
just open the question paper and then I'll have to look for the question paper
Yes, ma'am. Ma'am,
because I
whatever was given in the
what is
portal,
can you dictate the question?
that is question number 7 actually, and that was based on some log function, log and composite function.
Okay.
Yes, ma'am.
I don't have the question paper with me right now. You'll have to dictate the question. Can you?
Okay, yeah, ma'am. Please
Okay.
give me some seconds.
Okay.
Ma'am, am I audible?
Yes.
Yes, ma'am. So the question was, f of x is given to be log of, it was given to be log of log log of 5 of x. Like, ma'am, can you like share my screen?
No, you can just tell me the question.
Okay, so
Is it too long?
yeah, so f of x is given to be log of base 2 and then log of so inside that log function it is given that log of 3 I mean log of base 3, and then inside that log function it is given to be log of x to the base 5.
Is it this?
uh, yeah, ma'am, yes it is.
Okay.
And so one more function is given, that is that is g of x, which is equal to minus x square plus 10x plus 100.
We're talking about question
Uh,
7. Let me just find. I think I found the question paper. Let me just check where it is.
yes, ma'am.
Yeah.
Uh,
So
yes, ma'am. And h
then
of
you
x,
have
yes, ma'am.
FOG of x.
Yes, ma'am,
This will be
exactly.
log base 2, log base 3, log base 5, and then something here.
Yes, ma'am. And in question it is asked that what is the maximum value of FOG of x?
Okay. So your log base 2, all of these logs combined together are increasing functions, right? Till this one. This one is not an increasing function, but all these compositions are increasing. Log base 2 is an increasing function. Log base 3 is also increasing. Log base 5 is also an increasing function, right?
Yes, ma'am.
So for you to be able, for you to tell the maximum, to find the maxima, you need to find the maxima of just this function, and we're done, right?
Yes, ma'am. But ma'am, like we are so whatever the so the maximum value of g of x is that 5? I mean, at x equal to 5, are we getting the maximum value of g of x?
This is
Yes, ma'am. Be minus
you
b
get
by
minus 2x plus 10 here, then you equate it to 0, so you'll get x equals to 5, right? Yeah,
Yes.
you
Yes.
get it at 5.
But ma'am, this FOG of x, so 5 is not there in the domain. I have checked the domain of this function. 5 is not there. So how can we get the maximum value at 5?
What's the value at 5?
That is 0 actually, and the answer is given to be 0, but that is not in the domain of FOG of x. If we define the domain of fog x, then 5 is not there in the domain. The domain should be greater than 5,
Hmm.
strictly greater than 5.
The composition will be 1 second. Minus x square plus 10x plus 100. And this at 5 becomes minus 25 plus, if I'll put 5 here,
Yes.
this becomes minus 25, this becomes 50, and this is 100. And this should be 125. What's wrong? Why is it not in the domain?
Ma'am, can you define the domain of FOG of x?
If you see, you don't have to, if you have to go by the proper definition of the domain, it's basically x, which is in the first, it has to be in the domain of G. So it's domain of G intersected with x such that Gx is in the domain of F.
Mm-hmm. Yes, ma'am, exactly. So the domain of G is basically R, but uh, this part, so it is basically strictly greater than 5. This the right side of the intersection part.
This point is 5, right?
Hmm.
And the value that you get at 5 is 125.
Yes,
This
ma'am.
one.
Yes, ma'am.
You're saying only this part should be in the domain. Is it?
Uh, Ma'am, actually, I solved this, but I have got that the domain is 5 to infinity. I mean, the open interval 5 to infinity.
You have to check where this function is. The only condition that you have here is,
Mm-hmm.
okay, you have log base 5 here, right?
Hmm.
So for your log base 5 to be defined, you would want
Ma'am, actually, the domain of f is 0 to infinity, right? Or is it like, can you solve this inequality of this, right side part, the intersection? Yes, ma'am.
this one.
Yes, ma'am. Only
Yeah,
just
we'll do
this.
that. Okay. For your gx is, you want your gx to be in the,
Domain
and your
of,
gx is this entire thing, right? From 125 to everything, from minus infinity to 125, right?
Mhm.
This is it.
Hmm.
This is your range of G.
Yes, ma'am.
And then you you want this thing to be included in this domain of F. For
Yes,
domain
ma'am.
of F, you have log base 2, log base 3, and log base 5. And then we have X here. For this domain, you want first is you
X
want
should
X
be
greater than 0,
greater than 0.
right?
Yes, ma'am.
Then you would want log base 5x greater than 0, or
Hmm.
eventually you would want this thing log base 3, log base 5x greater than 0. This is one. Then log base 5x greater than 0 implies you will have x greater than 5 to the power 0, which is just 1.
Yes, ma'am.
So you want from this one, you want x greater than 1. And from here, log base 3, log base 5, x greater than 0. You would have this thing log base 5x greater than 1 and x greater than 5, right?
Yes, ma'am. So domain of
Just 1
G
second. If I'll have
is
5
is
here, we have 125. Then for 125, you'll have 3. And at 3, you'll have, okay, we'll have this 0 here. 1 second. We'll have 3 to the power 1. So log base 2, 1. And you can just have 0 here, right? But it works fine here. You can substitute x equals to, if you substitute x equals to 5 here,
Mhm.
we don't get any problem, right? We can find the value. That means it's in the
Yeah.
domain.
Yeah, but this so this is the domain. Okay, ma'am. But so if we define the domain of f o g of x, then it is not there, right? Because domain of G is basically R, and you intersect with this part x such that g of x is element of D domain of F. Then we are getting actually the x is element of 5 to infinity, right? I mean the open interval.
We
So
must have made a mistake somewhere. Let me just check again.
yes, ma'am.
For this, we want this part greater than 0.
Mhm. Log x to the base 5 is greater than 1, we can say.
Okay. Wait a minute. What we're doing wrong is, yeah, this for x should be greater than 5. So we'd want minus x square. What was it? What was that entire thing?
Plus
Minus x square.
10x plus 100.
Yeah. We'd want this thing to be greater than 5, right?
But ma'am, how we want this thing? Because x is strictly greater than 5, right? But how can we like make
This
this
is it.
inequality?
Okay. If you have this thing,
Hmm.
you have, let's say you have log and then something here, right? And if you
Mhm.
check the condition on x, you say your x should be greater than 0. Now, if you have log of x square plus 1, the condition on
Mhm.
x changes, right? You say x square plus 1 should be greater than 0, and then you will find the condition on x.
Okay.
So,
Okay,
by that
in
same
this
logic,
way, I
yeah.
understood, but like if we are asked to find the domain of FOG, then what would that be?
From here, you got x greater than 5. This is the definition we wrote, right? Domain of G intersected with x such that Gx is in the domain of F.
Yes, ma'am.
Yeah, so, okay. Your Gx is, what's your Gx? That's what we're saying. The condition on x is it should be greater than 5, right? And you want x such that minus x square plus 10x plus 100, if this was the quadratic equation, to be greater than this domain of F, which you found to be greater than 5, right? Or in simple words, your domain of F is from 5 to infinity, right?
But 5 is not included, right? Because that has to be strictly greater than
Okay,
0.
let's exclude 5 then. That's
Yes, ma'am.
fine. So if this is your domain of F and you want x such that Gx, this is Gx, right? Gx should be in this interval 5 to infinity. That means it's the same thing as saying this should be greater than 5, right? So you want x such that this expression is greater than 5. Is that okay? That's how you get this.
That's okay.
So you have to find the condition on x such that this expression is greater than 5. This expression is this. Your 5 might be somewhere here. You want to find the values where this is greater than 5. So, I mean, you don't even have to find that value. To
But
make
if,
sure that,
yes,
yeah,
ma'am. But if we are putting the x value as 5, then only we are getting the answer as 0. But we can't put the value as 5, right? Because that is not there in the domain of FOG.
no, 5 is in the domain of FOG.
But
It's not in the domain of F.
okay.
That's why I said this. If this is your function, your graph was like this, right? This value was 125 and it was attained at 5. And it looked like this. So at 5, your 125 is attained. You have to find x such that this function, that means this function, remains above the value 5, right? You want it above 5.
Okay.
So
Ma'am,
it's definitely somewhat
what
here,
is
right?
okay. What is the domain of FOG then?
For that, you'll have to find this. Domain of G was the entire R, right? What's G? Yeah, it's entire R. For this, let's do this. Can we factor this? Or actually, you don't even have to factor this. You'll have minus x square plus 10x plus 95 greater than 0. Now, what you do is, instead of solving this, just solve this, right? And you'll have roots. You'll find some roots here. Let's say these two are your roots. Then x such that this thing is greater than, you want this to be greater than 5. That means you want this thing to be greater than 0, right?
Yes, ma'am.
That means above this one. Sorry. So this is, that means it will be this value. So for, let's say this is A, this is B. These are the roots of this equation. Then from A to B, this equation is greater than 0, right? It's above
Yes,
x
ma'am.
axis. And for everything from minus infinity to A and B to infinity, it's less than 0, right? So just find
Yes,
the
ma'am.
root. My point is just find the roots of this equation. That's it.
Okay, ma'am. Ma'am, just now you have defined some intersection part, right? So according to that thing, what we are getting like the value of x just above. Can you scroll off?
There.
A little bit more. Yeah, here only. FOG of X.
This one,
Yes, ma'am.
that's what we did, right? This was, we've solved it here. This is what
Mhm.
we're solving. This set is the exact same as this one.
Okay, okay,
The exact same set. And for you
okay.
to solve this set, you will have to find the roots of this equation. Consider this a quadratic equation, find the roots of it. And those
Mhm.
roots, let's say A and B are the roots, then it will be A to B. So because you can't take A and B are going to give you 0, right? At
Mhm.
A and B, this equation will become 0, equal to 0. But we
Mhm.
want strictly greater than 0. That means exclude these 2 points, and everything between A and B will give you the value of this equation greater than 0 here, because it's on the positive x-axis.
Okay, 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 ma'am.
That's it. Is that okay?
Yes, ma'am. Ma'am, for this moment I am a bit confused, but I'll go through it once more, and if I
Yeah, okay.
get any problem, I'll post that in this course. Is that okay, ma'am?
Yeah.
Okay.
What's okay? I'll suggest you to go through this entire thing again. If there's a doubt, just post it on this
Yes,
course.
ma'am. Yes, ma'am.
If
Absolutely.
if you want me to go through this entire thing again, we can do that too.
Mm, No, ma'am. I mean, I
Okay.
don't want because I I have to go through it more thoroughly, so that is why.
Okay. All right.
Yes, ma'am. Okay, ma'am.
Does it?
Thank you.
Okay. Does anyone else want to ask anything else? Can we end this session here? Okay, I'll take that as a yes. So when ending this session here. Bye, guys.
Thank you, ma'am, for the session.
Thank you.